You see, for almost our entire lives, we walk around with a silent certainty that we never question. We know what time is, or at least we think we do. We feel it passing when we look at the clock, when we grow older, when we remember a summer that will never return. Time seems so obvious that we rarely stop to think about it. It moves forward, it flows, it goes from the past to the future. It marks a steady rhythm, like a universal metronome that we all share. And for thousands of years, no one saw any reason to doubt that. But here's the problem. That feeling, so solid, so natural, so intimate, begins to crumble the moment we try to measure time precisely. Not with intuitions, not with memories, but with clocks, with experiments, with numbers. And that's where everything breaks. Our relationship with time is deeply human. It is built from experiences, sunrise and sunset, hunger and satiety, birth and death. For us, time is a narrative. It has chapters, causes, and consequences. We always feel that there is a now, a special present, as if the entire universe were synchronized at that very instant with you. You are here. I am here. Everything is happening now. It seems obvious. But that obviousness is an illusion. For centuries, even great scientists shared this idea without questioning it much. Isaac Newton, for example, imagined time as a perfect, uniform river that flows the same for everyone, everywhere, regardless of what happens in the universe. An invisible backdrop against which reality unfolds. Absolute time. A kind of cosmic stage that never changes its pace. And if I'm being honest, that idea fits our everyday experience very well. When you look at your watch and someone else's, they both seem to agree. When you count the seconds, one follows another without surprises. Nothing seems strange. Nothing seems suspicious. Until we start measuring too carefully. Because measuring time is not as simple as it seems. Measuring time means comparing physical processes. There is no time floating in the air that we can capture. There are only things that change. A pendulum that swings, an atom that vibrates, a quartz crystal that resonates, a heart that beats. We say a second has passed because something has repeated a specific pattern. Time, at its core, is nothing more than a comparison between changes. And here the first crack appears. What happens if those changes do not behave the same everywhere? What happens if clocks, when subjected to different conditions, stop agreeing with one another? For a long time, no one thought that could happen. But when physicists began building increasingly precise clocks, atomic clocks capable of detecting differences of a tiny fraction of a second, something unsettling began to emerge. Clocks no longer matched perfectly when they moved differently, or when they were subjected to different physical conditions. Time, that old reliable friend, was beginning to behave strangely. Stephen Hawking put it with uncomfortable clarity. Time is not a primary notion that we understand intuitively, but a deep structure of the universe that we only begin to glimpse when we move beyond direct human experience. And our experience, unfortunately, is a terrible guide to understanding fundamental reality. Brian Greene insists on this point again and again. The human brain evolved to survive, not to understand the ultimate structure of the cosmos. We perceive time as a continuous flow because that is useful for hunting, fleeing, remembering, and planning. But usefulness does not mean truth. Imagine for a moment that you live on an island and have never seen the ocean from above. To you, the sea is flat, infinite, and uniform. There is no reason to think the earth is curved. Your experience deceives you not because you are foolish, but because you are limited by your perspective. The same thing happens with time. We feel that the present is something objective, a special point that separates the past from the future, a sharp edge that moves forward second by second. But when physicists analyze the universe with the same care with which we examine a map from the air, they discovered something disturbing. There is no universal now. There is no present shared by the entire cosmos. This idea is so counterintuitive that it is hard to accept even when it is explained calmly. We are so used to thinking of the present as something absolute that it almost feels offensive to imagine that two people might disagree about which things are happening at this moment. But physics does not negotiate with intuition. Taylor and Wheeler, in their exploration of space-time, make a key observation. What is truly fundamental are not instants, but events. Something happens, a flash, a collision, a birth. That is real. But the temporal order between events, simultaneity, the now, that depends on the observer. Let me put it another way. Two people who move differently can legitimately disagree about whether two events happened at the same time, and neither of them is wrong. This is not a mental trick. It is not an optical illusion. It is a deep feature of the universe. And when one encounters this idea for the first time, one usually tries to resist it, to think that there must be a hidden cosmic clock, a true time behind the scenes. But experimental evidence, again and again, destroys that hope. The present is not a universal line. It is a local construction. Brian Greene uses a powerful metaphor. Imagine that the universe is a massive block of space-time, a complete structure in which past, present, and future coexist as different regions of the same reality. You do not move through time. You advance along your personal trajectory within that block. Your sensation of flow is real, but it is not a fundamental property of the universe. It is a property of your consciousness. Time does not flow. We do. And this brings us to a deeply uncomfortable question. If the present is not universal, if time does not advance in the same way for everyone, then what exactly is that now we feel so strongly? The answer, according to modern physics, is as simple as it is unsettling. The now is a neurological illusion. Our brain constructs a sense of the present by integrating sensory information with immediate memory. It is a brilliant evolutionary trick. It allows us to react, make decisions, and feel continuity. But it does not reflect an objective boundary in the fabric of the universe. Hawking devotes entire pages to explaining how our perception of time is tied to the way the brain processes information, not to the fundamental structure of the cosmos. We remember the past because the past leaves physical traces. The future does not. That creates a psychological asymmetry that we mistake for a property of time itself. But physics finds no trace of a special now embedded in the equations. And the deeper we investigate, the worse it gets. Because even the concept of an instant begins to lose meaning. In the microscopic world, in the quantum domain, the notion of a perfectly defined moment becomes blurry. Events do not always have a clear order. Time stops being a clean sequence of frames and turns into something fuzzy, probabilistic, almost slippery. This does not mean everything is chaos. It means that our mental categories are too rigid for a reality that was not designed with us in mind. Human intuition about time fails because it assumes three things that are not true. First, that time is the same for everyone. Second, that there is a universal present. And third, that time flows as an independent entity. Each of these assumptions collapses when we look at the universe with precise instruments. And there is something deeply human in this story. For centuries, we believed we understood time because it never demanded much from us. But the moment we began to measure it with clocks capable of detecting tiny differences, time revealed its true nature: strange, flexible, observer-dependent. It is not that the universe is capricious. It is that we project our internal experiences onto a reality that operates by very different rules. This is only the first step. We have not yet spoken about motion, or velocity, or gravity. We have not yet seen what happens when someone moves at extreme speeds, or when space itself curves. But even here, at this initial point, there is already a conclusion that is impossible to ignore. Time is not what we thought, and the more we examine it, the more evident it becomes that this familiar sensation of living now is not a window into the heart of the universe, but an intimate reflection of how we are built. In the next stage of the journey, that initial crack will open completely, because when Einstein enters the scene, time stops being merely strange and begins to behave in ways that absolutely no one was prepared to accept. For a long time, even after we began to suspect that our intuition about time was fragile, there was still a secret hope. Perhaps, we thought, there exists a true time behind everything. An absolute time that imperfect clocks fail to capture properly. A kind of hidden pattern that the entire universe obeys, even if we do not know how to measure it precisely. That hope died at the beginning of the 20th century, and it died in a way so elegant, so simple, and so devastating that even today, it is hard to believe the universe had always worked this way without anyone noticing. This is where Einstein comes in, not as a magician, nor as an eccentric genius isolated from the world, but as someone who dared to take an uncomfortable question seriously. What really happens when we measure time? And yet, we are still far from understanding what the foam truly is. We do not know how it is organized. We do not know what laws govern its fluctuations. We do not know if the loops, filaments, or mini black holes that we imagine really exist. All we have are approximations, conjectures, and incomplete mathematical models. But what we do know is that black holes, in their extreme silence, force us to look toward that frontier. They are like spotlights, illuminating the deepest level of space. Every paradox, every inexplicable phenomenon, every limit where relativity breaks down, points us to the fact that the true answer lies there, where space ceases to behave like a continuous fabric. Quantum foam is the territory where the next scientific revolution will be born. It will be there that quantum gravity finds its final form. It will be there that information, time, and space cease to be independent concepts and merge into something more fundamental. And perhaps, when we understand that level, we will discover that all the reality we know, galaxies, stars, black holes, even ourselves, is an emergent consequence of that microscopic dance, like waves that appear solid but are nothing more than the surface expression of a much deeper ocean. There are moments in the history of science when the universe seems to stop to show us a glimpse of something we should not yet understand. A conceptual flash that appears as an intuition, a murmur at the limit of the thinkable. This happened when physicists began to suspect that reality might not be what it seems, that the three-dimensional world we inhabit could be, in a sense, a projection, not an illusion, but a representation of something more fundamental, a surface that encodes every detail of the volume we think we occupy. This intuition arose, curiously, not by looking toward galaxies, nor toward the beginning of the cosmos, but by studying black holes, objects so extreme that trying to describe them forces us to rethink the very foundations of existence. It is no exaggeration. Black holes put our traditional understanding of reality into crisis and opened a possible path toward a holographic universe. The idea is not poetic by accident. It is deeply mathematical. And it arises when we try to answer a question that seems innocent. How much information can a black hole contain? In physics, information is not a metaphor. It is a real, almost tangible measure. It represents the details that describe a system, the position of each particle, its energy, its quantum state, its possible interactions. It is the set of instructions that makes something what it is. Even a simple glass of water contains more information than we could record on all the computers on Earth. And when an object falls into a black hole, that information, in theory, should be stored somewhere. Not because we want it to, but because quantum mechanics requires that nothing be completely destroyed. The problem, as we saw before, is that the interior of a black hole does not seem to have enough space to store so much information, or at least not according to the classical view. But when Jacob Bekenstein began to analyze the issue, he discovered something surprising, almost disturbing. The amount of information a black hole can contain does not depend on the black hole's volume, but on its area. That is, not on what it occupies, but on its external surface, the event horizon. The larger the horizon, the more information the black hole can contain. But if we double its volume, the information does not double. It only increases according to the exterior area. Image illustrating the relation between black hole area and information/entropy. It is as if, somehow, all the complexity of the interior were encoded on its skin. A skin that is not a physical object, but a limit, a geometric boundary. This idea was so strange that many scientists initially did not know what to do with it. But it was correct. Again and again, the calculations agreed. A black hole's information grows with its surface. Hawking confirmed that the entropy, a measure of disorder or information, of the black hole also followed this rule. And there, without anyone explicitly searching for it, a principle was born that would forever change our understanding of the universe, the holographic principle. Leonard Susskind, one of the most passionate defenders of this idea, explained it in a way that seems straight out of a science fiction novel. The universe could function like a hologram. In a hologram, all three-dimensional information is encoded on a two-dimensional surface. And it is not magic, it is physics. A hologram works because every point on the surface stores data that reconstructs the depth, texture, and shape of what we see. If we apply this analogy to the universe, it means something extraordinary. The three-dimensional reality we experience could be a manifestation of the information stored on a more fundamental boundary. Not when we feel it, not when we remember it, but when we try to compare it using real physical instruments. Einstein started from something that, at first glance, seemed to have nothing to do with time. Light, the speed of light, an experimental fact that, at the time, was profoundly troubling for classical physics. All observers measured the same speed of light, regardless of how they were moving. Think about it carefully. If you are in a car and you throw a ball forward, someone standing on the sidewalk sees the ball moving faster than you do. That is common sense. That is what we expect. But when you do the same thing with a beam of light, that common sense breaks down. It does not matter whether you run toward the light, move away from it, or remain still. You always measure the same speed. For years, physicists tried to save the idea of absolute time by inventing hidden mechanisms, invisible media, structures that no one could detect. But each experiment eliminated one more possibility, until Einstein took a radical step. Instead of adjusting light to time, he adjusted time to light. And that is where the real earthquake began. Einstein understood something that seems simple once it is said, but that changes everything. Measuring time is measuring when events occur. And measuring when events occur requires clocks. But those clocks are not abstract entities. They are physical objects that exist in space, that move, that interact with the universe. If motion affects physical processes, then it must also affect clocks. This idea, taken to its ultimate consequences, destroys the notion of absolute time. There is no privileged clock. There is no special observer. Each observer carries their own time with them. Taylor and Wheeler insist on this point with almost brutal clarity. Time is not something that exists by itself. It is something that is measured along trajectories. And those trajectories depend on motion. Here, a fundamental concept appears that will completely change the way we talk about time: the event. An event is something that happens at a place and at a moment: a flash, an explosion, the tick of a clock, the birth of a star. All observers, without exception, agree that the event occurred. No one disputes that. But what they do not all share is the when. Two observers can assign different times to the same event and both be right. Taken seriously, this statement is deeply unsettling. We are used to thinking that disagreement about time is a measurement error, a flaw in the instrument. But in relativity, the disagreement is real. It is not an imprecision. It is a feature of the universe. Imagine two people observing the same scene from different states of motion. Each has a perfectly calibrated clock. Each follows the laws of physics. Yet, when they compare their measurements, they discover that they do not match. Not because one is broken, but because time itself has behaved differently for each of them. Here is where the idea of relativity becomes literal. Time is relative to the observer. Brian Greene explains this masterfully by reminding us that the question, "What time is it now?" only makes sense if you specify for whom. Without a concrete observer, the question has no physical meaning. And this forces us to abandon a deeply ingrained assumption, that we all share the same present. Einstein showed that simultaneity is relative. Two events that occur at the same time for you may not be simultaneous for someone moving relative to you. There is no universal method for synchronizing clocks that works for all possible observers. This point deserves a pause, because it is one of the hardest blows to our intuition. The idea of simultaneity seems so basic that it is difficult to imagine a world without it. But as soon as we incorporate the finite speed of light and the equality of its measurements, simultaneity dissolves. Clocks stop agreeing not out of caprice, but because the universe offers no unique way to coordinate them. Taylor and Wheeler propose an approach that becomes liberating once you accept it. Stop obsessing over time as something global. Focus on the local, on what happens along a specific trajectory, on the time marked by a clock that accompanies an observer from one event to another. That time is absolute, but it is absolute only for that observer. This time is called, very appropriately, proper time. It is the time measured by the clock that goes with you, the time that ages with you, the time that no one else can dispute. And here emerges one of the strangest revelations of modern physics. Two people who depart from the same event and meet again later may have lived through different amounts of time. This is not a metaphor. It is not an illusion. It is a real, measurable difference, confirmed experimentally. Hawking emphasizes that this discovery did not arise from philosophical speculation, but from a logical requirement. The laws of physics must be the same for all observers. There is no privileged frame. There is no correct point of view from which to measure true time. The universe offers no hierarchy of observers. This forces us to radically change the way we think about time. It is no longer a universal line that runs through the entire cosmos. It is a collection of local times, woven together with space, forming a unified structure, space-time. And this change is not just conceptual. It has practical consequences, consequences that today affect real technologies, navigation systems, satellites, global communications. All of these work because we accept that clocks do not agree, and we correct those discrepancies using relativity. But even setting applications aside, the philosophical impact is enormous. If there is no absolute time, then the question, what is happening now elsewhere in the universe, loses its universal meaning. There is no cosmic now that we can point to. There are only local nows defined by each observer. Brian Greene describes this discovery as the end of time as a backdrop. Time stops being the passive stage on which things happen and becomes a dynamic actor dependent on motion and context. And here, something fascinating happens. At first, this idea feels uncomfortable, almost offensive. It seems to take something fundamental away from us, but over time it begins to feel strangely coherent. The universe stops imposing a single perspective and accepts all valid perspectives. There is no privileged point of view because it does not need one. This is one of the moments when modern physics shows a deep humility. It does not say that our experience is false. It says that it is local, partial, valid in its context, but not universal. Our clock works. Our time flows. Our life has duration. All of that remains true. What ceases to be true is that this impersonal experience can be elevated to a cosmic law. Einstein did not destroy time. He freed it from the illusion of universality. And what emerged in its place was something far more subtle and powerful, a structure in which events, observers, and clocks are intertwined, where each trajectory has its own rhythm, where disagreement is not an error, but an essential feature. At this point in the journey, we can no longer cling to the idea that time is the same for everyone. That notion is behind us. Now we know that time depends on motion, on the path taken, on the history of each observer. But we have not yet seen how far this idea goes. Because what is truly unsettling is not only that clocks do not agree, it is that this disagreement grows in extreme ways when motion intensifies, when velocities approach fundamental limits, when space and time begin to mix in ways that challenge all intuition. In the next stage, time will stop being merely relative and will begin to stretch, contract, and deform in a way that forever transforms our understanding of what it means to live, to endure, and to exist in the universe. Let me ask you something before we continue. For a moment, stop imagining time as one thing and space as another. I know it sounds strange, because we have spent our entire lives separating them. Here I am in a particular place. Time passes here, second by second. Two different concepts, two different words, two separate mental boxes. That is how we were taught. That is how it feels. But that separation is artificial. It is a mental convenience, and when Einstein broke it, nothing was ever the same again. Until the early 20th century, even after accepting that time was not absolute, people still thought that space and time were separate stages. Space was where things happened. Time was the clock that marked when they happened. They could interact in strange ways, yes, but they were still independent entities. The great conceptual leap was realizing that this does not work. It does not work because measuring time always involves measuring space, and measuring space always involves measuring time. You cannot separate one from the other without breaking the coherence of the laws of physics. Think of something as simple as saying, that event happened at 10 o'clock at night. Where did it happen? You cannot answer with just a time. You need a place, and if you say, it happened there, that is not enough either. You need to know when. Every real event in the universe has 4 inseparable coordinates, 3 of space and 1 of time. Taylor and Wheeler insist on this with almost pedagogical clarity. Reality is not made of spaces that evolve in time, but of events situated in space-time. The historical mistake was thinking that time was something external that flowed over a fixed spatial stage. Reality is deeper. The stage and the clock are the same thing. Here is where the concept that changes everything is born: space-time. It is not a metaphor. It is not a poetic way of speaking. It is a real physical entity, a geometric structure that unites what we once thought separate. Space-time is not space plus time. It is something new, something that only exists when the two fuse. To help you visualize it, imagine a map. Not just any map, but one that shows not only places, but moments as well. Each point on the map does not just say here, but here and now. That map does not unfold in 2 dimensions, but in 4, and you are not standing still on it. You are tracing a trajectory. That trajectory is your life. From the instant you are born to the instant you die. You trace a line through space-time. You do not move only through time. You move through space-time as a whole. Even when you are sitting still, apparently motionless, you are still moving through this structure. Always, without exception. And here appears an idea that often surprises even those who already know something about relativity. There is no absolute rest. You are never truly still. If you are not moving through space, you are moving as fast as possible through time. And if you move through space, you inevitably reduce the rate at which you move through time. This is not an analogy. It is a real relationship. Brian Greene explains it very visually. We are all traveling through space-time at a constant speed. You cannot change that total speed. You can only redistribute it. More spatial motion means less temporal advance. Less spatial motion means more temporal advance. This is radical, because it means that time is not something that simply passes while you move. Your motion through space directly affects your experience of time. Before Einstein, this would have sounded absurd. After Einstein, it is unavoidable. Space-time imposes a new geometry on the universe, a geometry in which time is not an external parameter, but another dimension. One with different properties, yes, but inseparable from the rest. It is not simply a line running parallel to space. It is woven into it. And when you accept this, many things begin to fall into place. For example, the fact that there is no universal simultaneity ceases to be a mystery. Different observers trace different slices of space-time. What is now for you corresponds to a different section of the structure than it does for another person in motion. not because the universe is confused, but because the geometry allows it. The present is not a universal layer of the cosmos. It is a geometric choice. This is deeply disconcerting at first, because we feel the present the way we feel our own body, as something immediate, unquestionable. But physics tells us something uncomfortable. That sensation does not come from the structure of the universe, but from how we navigate through it. Hawking points out that the great intuitive mistake was to think that time had a privileged role. In reality, the privilege belongs to space-time as a whole. The fundamental laws do not distinguish between past, present, and future in the way our experience does. They distinguish trajectories, intervals, causal relationships. Here, another key concept appears: the space-time interval. Two observers may disagree about the spatial distance between two events. They may disagree about the time elapsed between them, but they will always agree on the space-time interval. That quantity is invariant. It is the true measure of separation in the universe. This is profoundly elegant. Where there was conflict before, unity appears. Disagreement between clocks is not a problem. It is a clue. A sign that we are measuring reality incorrectly if we insist on separating space and time. When you unite them, everything falls into place. And here, something important happens for you as a viewer. This is not just a story about equations and abstract theories. It is a story about your own existence, because you do not live in space or in time. You live in space-time. Every decision you make, every step you take, every beat of your heart is a movement within this structure. You are not waiting for time to pass. You are traveling along a unique trajectory that no one else can travel for you. And we have not yet reached the most unsettling part. Because if space and time form a single entity, then deforming one implies deforming the other. And that opens the door to consequences that go far beyond motion, consequences that involve extreme velocity, energy, and, later on, gravity. In the second part of this section, we will see clearly something that is often said vaguely, but has a very precise meaning. Moving through space changes your relationship with time, not as a poetic metaphor, but as an unavoidable physical law. And when you understand this, the universe stops being a place where things happen with time passing quietly in the background, and becomes a dynamic structure in which every movement has a temporal cost. Now I want you to imagine something very concrete, not a spaceship, not a laboratory experiment, not something distant. Imagine yourself walking, one step, another step. It does not seem like much, just a few meters, nothing spectacular. But even in that everyday gesture, you are doing something extraordinary. You are redistributing your motion in space-time. When you move through space, even slowly, you are modifying the way you advance through time. The effect is tiny, imperceptible to your body, but it exists. And that is what is truly unsettling. The universe makes no exceptions. The relationship between space and time always holds. Einstein did not discover this because he wanted to complicate physics. He discovered it because there was no other coherent way to describe reality. If space and time are a single entity, then motion cannot affect only one of them. It affects both. And this leads to an inevitable conclusion. Time does not pass the same for everyone, because no one moves through space-time in the same way. Taylor and Wheeler express this in a way that deserves to be savored slowly. They say that we do not age because time passes, but because we traverse a certain length of our trajectory in space-time. Aging is not an external process. It is a geometric measure. You age because you follow your path. This perspective completely changes how we understand the famous time dilation. It is not that time slows down magically when you move fast. It is that your trajectory tilts differently within space-time, and that tilt makes the temporal length of your path different. It is not punishment. It is not an anomaly. It is geometry. Brian Greene uses a powerful image to help you internalize this. Imagine space-time as a vast plain with hills and valleys. Different routes between 2 points can have different lengths, even if they start and end in the same place. The time you experience depends on the path you take. 2 people can set out together and meet again later, having lived through different durations, not because one skipped time, but because they traveled a different route. This is no longer speculation. It is a verified fact. Atomic clocks carried on airplanes, satellites orbiting the Earth, subatomic particles moving at extreme speeds, all confirm the same thing. Motion through space alters the rhythm of time. But here is something even deeper, something that is often overlooked. Time does not slow down from the outside. Each observer always experiences their own time as normal. There are no strange sensations, no clocks that seem defective. Your time always feels right to you. That is crucial, because it reminds us that there is no privileged point of view. No one lives in a false time. We simply live in different times. Hawking emphasizes this point carefully. Relativity does not say that time is illusory. It says that time is local, real, but not universal. Each observer is entitled to their own clock, and nature respects that. The real mistake was believing that there had to be a master clock of the universe. When we abandon that idea, many paradoxes disappear. The famous twin paradox, for example, stops being a logical puzzle and becomes a direct consequence of different trajectories in space-time. There is no trick. There is no contradiction. There is geometry. To move through space literally means to move differently through time. And here I want to speak to you directly, not as a reader of physics, but as a human being. This idea has a quiet but powerful existential consequence. Your life is not a succession of instants being used up. It is a complete shape, a unique trajectory that no one else can repeat. You are not waiting for time to pass over you. You are building your path. Space-time does not push you. It supports you. This even changes how we think about the future and the past. They are not places that no longer exist or do not yet exist in an absolute sense. They are different regions of space-time, causally related to your present, but not privileged by any cosmic label. The universe does not mark the now. You do. And the more you move, the more you change your relationship with space, the more your relationship with time changes. In everyday life, we do not notice this because our speeds are ridiculous compared to the scales at which these effects become dramatic. But the principle is the same. There are no exceptions. This understanding prepares the ground for something even more surprising. Because if motion alters time, and if space-time is a real physical entity, then not only motion can deform it. Mass, energy, and gravity can do so as well. And when that happens, time stops being merely relative and begins to curve. But before we get there, it is important that this idea be firmly engraved. Space and time are not two separate ingredients of the universe. They are a single structure. And moving within it means sacrificing time in exchange for space. This is not poetry. It is the deep architecture of reality. I want you to imagine something very concrete. Not an equation, not a distant experiment, but a simple scene. Two identical clocks, placed side by side. Both show exactly the same time. Both work perfectly. Now, without doing anything strange, without tricks, we take one of those clocks and put it on a ship that will travel very fast. The other stays with you here, in relative rest. Before Einstein, no one would have expected any surprise. When they met again, both clocks should agree. Time, after all, was the same for everyone. But the universe had other plans. When the traveling clock returns, something has changed. It shows less time elapsed. It is not broken. It has not fallen behind due to mechanical flaws. It has simply lived less time. And the most unsettling part is this. The clock that traveled noticed nothing strange. For it, every second was normal. Every tick occurred with the same regularity as always. Time did not slow down from the inside. It simply behaved differently when compared with the other clock. This is where time dilation stops being an abstract idea and becomes a concrete experience. Because, at its core, a clock is nothing more than a simplified version of ourselves. It is a physical system that ages, that changes, that accumulates duration. When we say that a clock shows less time, we are saying something deeper. Less physical change has occurred in it. Taylor and Wheeler explain this with disarming clarity. Proper time is the time measured by the clock that accompanies the observer, and that time depends on the path taken through space-time. There are no conceptual shortcuts. There are no exceptions. A clock that moves along a different trajectory measures a different duration. Now I want you to replace the clock with a person. Imagine two identical twins. Born on the same day, they grow up together, share childhood, memories, laughter. One day, one of them boards a ship that travels at extreme speeds, while the other remains on Earth. Years later, the ship returns. The two meet again, but they are no longer the same. The traveling twin is younger. This story has been told so many times that it feels like a science fiction cliché. But here is the key. It is not science fiction. It is a direct consequence of the geometry of space-time. And most importantly, it has been experimentally verified. Not with people, of course, but with atomic clocks, subatomic particles, satellites, and airplanes. The result is always the same. The time lived depends on motion. Brian Greene insists on something that is often misunderstood. It is not that one twin sees the other age faster during the trip. That would be a visual confusion. What matters is not what is seen, but what is measured when both are back together and compare their clocks. And there is no possible dispute. One has lived less time, not by magic, not by philosophical relativism, but because their trajectory through space-time was different. This point often generates emotional resistance. We find it hard to accept that aging is not a universal process, that there is no absolute age independent of the history of motion. But the universe does not seem interested in protecting our intuitions. Hawking emphasizes that this phenomenon violates no deep law. On the contrary, it is an inevitable consequence of demanding coherence between the laws of physics and the constancy of the speed of light. Refusing to accept time dilation would require accepting far worse contradictions. Here is something important I want you to notice. Time dilation is not an optical illusion or a psychological effect. It does not depend on perception, signal delays, or synchronization tricks. It is a real, physical, cumulative effect. The faster you move, the less proper time elapses for you between two events. There is no escape. Now imagine a ship that approaches closer and closer to the speed of light. No matter how much thrust it has, No matter how much energy it consumes, it can never reach that speed. But the closer it gets, the more dramatic the time dilation becomes. From the outside, it looks as if time on the ship slows down more and more. From the inside, everything remains normal. Clocks work, hearts beat, thoughts flow. The traveler feels nothing strange. And yet, upon returning, they discover that the external universe has advanced far more than they have. This is not a paradox. It is a geometric asymmetry. Taylor and Wheeler emphasize that the key lies in trajectories. Not all paths between two events are equivalent. The straight path in space-time maximizes proper time. Paths that involve accelerations and changes of direction reduce the duration lived. This breaks another deep intuition. We tend to think that moving more makes more things happen. But in space-time, the opposite is true. Moving a lot through space means sacrificing time. Here, everyday experience betrays us. On our human scale, the effects are so small that they seem non-existent. But the principle is universal. Every step you take, every displacement, every trip by car or plane modifies, however minutely, your proper time. This is not a metaphor. It is a physical fact. And here an inevitable question arises. If all this is real, if it has been measured, if it is not science fiction, why don't we notice it? The answer is simple and humbling. Because we are slow, ridiculously slow compared with the scales at which space-time reveals all its strangeness. Our speeds are a tiny fraction of the speed of light. The effects exist, but they are buried beneath layers of everyday insignificance. However, when engineers design systems that depend on extreme precision, these effects cease to be negligible. Navigation satellites, for example, must correct for time dilation in order to function properly. If they didn't, errors would accumulate rapidly. Relativity is not optional. It works, whether you like it or not. And here is something deeply revealing. Time dilation is not a punishment for moving fast. It is a manifestation of the fact that time is not a universal resource consumed equally by everyone. It is a dimension that responds to motion. It's not that time stretches. It's that you traverse less time. This change of perspective is crucial because it allows us to abandon the idea of time flowing like an external river and begin to think of time as a length, a distance measured along your life. In the second part of this section, I want to take you a bit further, not only to ships and clocks, but to the human experience of travel, of return, of falling out of sync with a world that moves on without you. Because time dilation doesn't just challenge classical physics, it also challenges the way we think about the future, waiting, and what it means to live in a universe where time is not the same for everyone. Now I want you to imagine the return, not the journey, not the speed, not the ship crossing space. The return, the door opening, the reunion, the moment when you compare your clock with that of the world you left behind. That is the instant when time dilation stops being a concept and becomes an existential experience. Because while you were traveling, the universe did not wait for you. Brian Greene describes this moment with a mix of precision and wonder. The traveler has done nothing wrong. He has not cheated time. He has not escaped reality. He has simply followed a different trajectory through space-time, and that trajectory has granted him less duration. The world he returns to has aged more. Here appears one of the most unsettling consequences of relativity. One person's future can be another's past. Not in a fantastical sense, but in a geometrical one. Two observers can separate, and reunite, having lived radically different amounts of time, even though both followed perfectly normal physical laws. This forces us to rethink what we mean by time travel. It's not about jumping backward or violating causality. It's about moving toward the future at different rates. And that, I insist, is not fiction. It is a direct consequence of how space-time works. Hawking emphasizes that time dilation does not allow classic paradoxes. You cannot go back and meet yourself in the past. The causal structure of the universe remains intact. What changes is the relationship between duration and motion. The traveler does not step outside of time. He simply accumulates less proper time. And here I want to speak to you with complete honesty. This idea has something profoundly poetic and something profoundly disturbing about it. Poetic, because it shows us that the duration of a life is not a fixed number dictated by the cosmos. Disturbing, because it reminds us that not all paths lead to the same when. Two people can depart together and end up in different futures. Taylor and Wheeler emphasize that this difference does not depend on perception, but on physical history. Lived time is an objective property of the path taken. There is no negotiation. And yet, from the inside, everything feels normal. That is the most disconcerting detail of all. The traveler does not feel time slow down. He does not experience longer seconds or slower thoughts. Everything unfolds with the same subjective cadence as always. Relativity does not steal experiences. It redistributes durations. This destroys another deeply human intuition. The idea that time is something external that pushes us forward. In reality, it is we who move through a structure that does not distinguish between space and time in the way our minds do. Time does not pass you, you pass. When you accept this, time dilation stops seeming like a strange trick and starts to look like a natural consequence. If space and time form a single entity, why should it surprise us that moving through one affects the other? The real mistake was expecting time to be immune to motion. Now, it's important not to exaggerate. Time dilation is not a practical tool for extending human life in any everyday sense. The required energies, the extreme speeds, the biological limitations make these effects irrelevant for daily life. But that does not make them any less real. We live in a universe where time is not a uniform ribbon, unrolling the same way for everyone. We live in a universe where each trajectory tells a different temporal story. And here is one final reflection I want to share with you before closing this section. Relativity does not tell us that time is arbitrary. It does not say that anything goes. On the contrary, it imposes strict rules, precise relationships, unbreakable limits. Time is flexible, but not chaotic. Time dilation is not an anomaly. It is a signal that the universe is built in a richer way than our intuition allows, a way in which the duration of a life depends not only on how many days pass, but on how they are traversed. In the next section, we will introduce a new force into this story, one that depends not only on motion, but on mass, energy, and the very shape of space-time. When gravity enters the scene, time does not merely dilate, it curves. And there, the universe once again shows us that even what we believe to be most intimate and constant can behave in ways we never would have imagined. I want you to make a small mental effort with me. Nothing technical, nothing abstract, just a simple scene. Imagine that you are here, right now, reading these words. At the same time, somewhere very far away, another person is also living their own now. Instinctively, without thinking, you assume that both nows coincide, that they are part of the same universal instant, that, somehow invisibly, the entire universe is synchronized with you. That idea is so deep, so automatic that we rarely question it. We live convinced that a shared present exists, an invisible plane slicing the universe into two clear halves, what has already been and what has not yet occurred. You are on that edge, I am on that edge. Everyone is there. But that image, so comforting, is false. Not approximately false, not technically false, radically false. Simultaneity, as you imagine it, does not exist. And the most unsettling part is not that it fails in extreme situations, in black holes or interstellar travel. It does not exist even in principle. The universe recognizes no absolute now. It never has. This discovery was not a minor detail of relativity. It was one of the hardest blows Einstein dealt to our intuition, because it forces us to accept something almost offensive to human experience. Two people can live in the same physical universe and yet not share the same present. Not because one is wrong, not because one has delayed information, but because the very concept of simultaneity depends on the observer. To understand this, we must abandon a very old mental habit, the habit of thinking that time is a kind of universal conveyor belt, advancing uniformly for everyone. That image works well in everyday life, but it collapses when we examine how time is actually defined in physics. Time is not defined by asking what is happening now, but by asking what events occur and how do we measure them. And measuring implies signals. It implies light. It implies motion. This is where everything begins to come apart. Suppose you try to decide whether two distant events occurred at the same time. You cannot be in both places at once. You need to receive information. That information travels at a finite speed, the speed of light. No matter how fast you think, you cannot receive both signals instantaneously. For a long time, it was assumed that this delay was merely a practical problem, that, deep down, a real simultaneity existed, even if we could not detect it with perfect precision. Einstein refused to accept that assumption. He said something far more radical. If there is no physical way to define a universal simultaneity, then it makes no sense to say that it exists. There is no deep down. This is not philosophy. It is an operational demand. If a concept cannot be defined by real physical procedures, that concept does not belong in the fundamental description of the universe. Absolute simultaneity fails that test. Imagine two lightning strikes hitting opposite ends of a railway track. For a person standing exactly at the center, both flashes arrive at the same time, and they conclude that the strikes were simultaneous. But another person, moving relative to the track, receives one flash before the other. According to their measurement, the events were not simultaneous. Before Einstein, one would have said that one of the observers was mistaken, that the real simultaneity existed independently of them. Einstein eliminated that hierarchy. Both observers are entitled to their measurement. Both are correct. There is no cosmic referee to decide who is right, and this is where human experience begins to crack. Because if two observers can legitimately disagree about what happens at the same time, then the present ceases to be a universal entity. There is no clean slice of the universe that everyone shares. Brian Greene expresses this with a powerful image. Each observer draws their own slice of space-time. That slice defines what they consider the present. But different slices cut the structure in different ways. There is no single correct way to do it. The present is a geometrical choice, not a property of the universe. And I want you to feel this, not just understand it, because this idea is not a technicality. It directly affects how you locate yourself in the cosmos. When you think about the now of a distant star, a faraway galaxy, or someone living elsewhere in the universe, you are projecting your local present onto a reality that does not share it. There is no physical fact that determines which distant events are simultaneous with you at this instant. Your now does not extend to them. This does not mean that the universe is chaotic or subjective in a trivial sense. It means that the structure of space-time does not privilege any set of instants as the true present. Each observer has their own present. All are real. None is privileged. Here arises a consequence that often causes deep discomfort. If no universal simultaneity exists, then the past and future of other observers can mix in unexpected ways from your point of view. Events you consider future may be past for someone moving relative to you. Not because time is broken, but because the idea of an absolute temporal order was never correct. Taylor and Wheeler emphasize that the one thing that remains firm is causality. The universe jealously protects the relationship between cause and effect. You cannot influence events outside your causal cone. You cannot send information to the past. But within those limits, the temporal order of distant events is not uniquely fixed, and this is crucial. The universe does not collapse into contradictions because causality remains intact. What collapses is our idea of a global present. For the human mind, this is almost intolerable. We build ourselves around the idea of a shared now. Our conversations, our memories, our social expectations depend on it. But physics is not obliged to respect our psychological needs. The present is an experience, not a layer of the cosmos. Hawking insists that this rupture is not a flaw in the theory, but a revelation. For centuries, we confused the structure of our consciousness with the structure of the universe. We thought the world had to be organized around how we experience it. Relativity forces us to accept the opposite. Our experience is local, partial, adapted to small scales and low speeds. The universe is larger. Now I want you to think about something even more disturbing. If no universal present exists, then the universe does not evolve in the way we usually imagine. There is no global state changing in synchronized fashion. There is no current moment of the cosmos. The universe as a whole is not passing through time. It is extended in space-time. This does not mean that everything is predetermined or that change is illusory. It means that change is a relationship between regions of space-time, not a universal parade of instants. You experience change because you traverse your trajectory. Others traverse theirs. This is where many people feel vertigo, because this idea seems to erase the boundary between past, present, and future. And in a certain sense, it does. Not as absolute categories, but as relationships that depend on the observer. The future is not a privileged region that does not yet exist for the entire universe. It is simply a region of space-time that is not yet causally connected to you. For other observers, it may be. This does not make time illusory. It makes it relational. And here I want to involve you directly. When you think about your life, you imagine it as a sequence. Yesterday, today, tomorrow. That sequence is real for you. It is your trajectory. No one invalidates it. But it is not a universal structure that applies to the entire cosmos. Your present is real, but it is yours. It is not a property of the whole universe. This discovery even changes the way we talk about what is happening right now in the universe. That phrase, so common in popular science, is technically incorrect. There is no universal right now to refer to. Every such statement implicitly depends on an unmentioned observer. Simultaneity does not disappear because the universe is capricious. It disappears because we try to impose on it an organization it does not need. And yet, we go on living as if it existed. Because at our scale, the difference is negligible. Our relative speeds are small. Our distances are modest. The disagreement between presents is so tiny that it dissolves into everyday experience. But the fact that we don't notice it doesn't mean it isn't there. Relativity teaches us an uncomfortable and deeply human lesson. The universe is not organized around us. It does not offer us a central point of view. It does not grant us a privileged now. It allows us to exist, nothing more. And that is enough. When you accept that two people can inhabit the same physical universe without sharing the same present, something breaks, and something is set free. The illusion of centrality breaks. The understanding is freed that reality is richer, more flexible, more expansive than our immediate experience suggests. There is no absolute present that the universe must respect. There are observers, events, and relationships, and this prepares the ground for the next conceptual leap. Because if time is not universal, if simultaneity does not exist, then gravity, that force we always believed to be so familiar, cannot remain what we thought it was. When gravity enters the scene, space-time ceases to be merely a geometric stage. It becomes something that curves, deforms, and directly affects the rate of time. And there, the concept of now does not merely dissolve, it fragments even further. But before reaching that point, it is important that this idea be firmly engraved. We do not share a universal present. We share a universe, yes, but we traverse it along different trajectories, with different clocks, with different presents. And the universe, indifferent to our nostalgia for synchrony, functions perfectly well that way. I want you to forget for a moment everything you've been told about time as something that passes, not as a current that carries you along, nor as an invisible clock advancing from the outside. I want to propose another image, one far more faithful to what physics has discovered. Time is not something that flows over you. Time is the path you travel. Your life does not occur within time. Your life is a trajectory in space-time. This idea is one of the deepest changes introduced by relativity, and curiously also one of the quietest. It rarely appears in headlines or catchy phrases, but when you truly understand it, it completely transforms the way you place yourself in the universe. Because an external time that measures you disappears, and something far more intimate appears, your own path. In classical physics, time was a universal axis. All objects moved through space, while time advanced the same for everyone. Relativity breaks that image. Instead of a shared temporal axis, a complete structure appears in which every object, every person, every particle traces its own path. That path is called a world line. This is not a metaphor. It is a real geometric entity. A world line represents the complete history of an object in space-time. Each point on that line is an event, something that happens at a place and a moment. Your birth is one point. This instant in which you are reading these words is another. Your final day, whatever it may be, is there as well. All those events are connected by a continuous line. That line is you. And here is what matters. No two world lines are the same. Even if two people are born together, live together, and die together, their trajectories never coincide exactly. There are always microscopic differences in motion, acceleration, interaction with the environment. Each world line is unique, unrepeatable, like a cosmic fingerprint. Taylor and Wheeler insist that this is the correct language for talking about time. Not abstract seconds, not universal instants, but trajectories, paths taken through space-time. The time that matters is not what a distant clock reads, nor what appears on a global calendar. The time that matters is the length of your own world line. That is called proper time. Proper time is the time you experience, the time that ages with you, the time measured by the clock you carry with you, whether a mechanical clock, an atomic clock, or your own body. And that duration does not depend on opinions or external observers. It depends only on the path you follow. Here, a very common confusion disappears. It is not that different observers see different things, and then we have to decide who is right. Everyone is right along their own trajectory. The clock that accompanies a world line always measures its duration correctly. It cannot be wrong because there is no external standard it must be compared against. The clock you carry with you always has the final word because it measures something profoundly objective, the length of your path through space-time. This may sound abstract, so let me bring it closer to your experience. Think of a journey, not the time shown on the station clock, but the time you feel has passed for you. Two people can leave the same place and arrive at the same destination by different routes. One takes a straight path. The other makes detours, stops, changes direction. Both arrive at the same final point, but they have traveled different distances. In space-time, something analogous occurs, though with a crucial difference. The straightest path is not the one that minimizes duration, but the one that maximizes it. The path followed by an object that experiences no unnecessary accelerations, that moves inertially, is the one that accumulates the most proper time. This overturns a deeply rooted intuition. We are used to thinking that moving more means living more time. In space-time, the opposite happens. The more you deviate, the more you accelerate. The more you change direction, the less proper duration you accumulate. It is not punishment, it is geometry. Brian Greene explains that space-time has a structure such that proper duration depends on the shape of the path, not only on the starting and ending points. Two trajectories that connect the same events can have different temporal lengths, and that difference is real, measurable, and cumulative. This is what makes time dilation not a visual effect or an illusion. It is not that, from the outside, a clock appears to run slower. It is that its world line is shorter in the temporal sense. It has traversed less time. Here, a profoundly liberating idea appears. The time you live cannot be taken from you. It does not depend on external clocks or social conventions. It depends on your real physical path. The universe does not keep a central ledger of seconds. Each world line keeps its own. Hawking emphasizes that this approach eliminates many apparent paradoxes. When we stop thinking of time as something global and start thinking of it as proper duration, the contradictions disappear. There are no wrong clocks. There are different trajectories. The clock you carry with you does not need to synchronize with the universe. The universe has no master clock. This has subtle but profound consequences for how we understand life itself. Your age is not an absolute property floating in the cosmos. It is a measure of how much space-time you have traversed. It is a geometric property of your existence. Two people can have the same chronological age according to a calendar, and yet not have lived exactly the same proper duration if their trajectories have been different. In everyday life, the difference is negligible, but in principle, the universe guarantees no equality. And here I want you to pause for a moment, because this idea touches something very intimate. We always talk about time as something that slips away from us, as something we lose, as something that pushes us toward the end. But from this perspective, time is neither lost nor gained. It is traveled. You are not a passive object carried along by a temporal current. You are an active traveler tracing a line through space-time. Every decision you make, every movement, every acceleration, every moment of rest subtly modifies the shape of that line, not only in space, but in lived time. This does not mean that you have practical control over your duration in everyday terms. The differences are minuscule on a human scale. But conceptually, it is a revolution. The duration of your life is not a universal counter running down. It is the length of a unique path, and that path cannot be measured from the outside with greater authority than from within. Taylor and Wheeler insist that proper time is the only time that admits no dispute. Other observers can assign different coordinates, different times, different simultaneities, but proper time is invariant. Everyone will agree on it when results are compared. The clock that travels with you does not need to defend itself. The geometry of space-time stands behind it. This is where many people feel a strange mixture of relief and vertigo. Relief, because the idea of an external time that judges or pressures us disappears. Vertigo, because the universe ceases to offer a comforting global reference. There is no cosmic clock marking the correct rhythm. There are billions upon billions of clocks, each following its own path. And yet, the universe does not disintegrate into chaos. Because even though there is no absolute time, there is a rigorous structure that connects all trajectories. Causality remains intact. The relationships between events follow precise rules. Space-time is not arbitrary. It is flexible, but coherent. When you understand time as trajectory, many questions change their form. You no longer ask, how much time really passed, but rather, what path was taken? You no longer seek a universal present, but relationships between worldlings. Time ceases to be a backdrop and becomes a property of motion. And here, a quiet but powerful conclusion emerges. No one lives more time in an absolute sense. No one lives less in a moral or metaphysical sense. Each person lives their duration, inscribed in their trajectory. The clock you carry with you is not a secondary instrument. It is the final arbiter, not because it is subjective, but because it measures exactly what matters. Your proper time, not the time of others, not the time of the universe, yours. Now I want you to forget about high speeds, about ships, about extreme journeys. I want you to imagine something far more everyday, something you have felt all your life without thinking much about it. Your weight. The simple fact of standing on the ground. The constant sensation that something pulls you downward. What we call gravity. For centuries, gravity was understood as just another force. Invisible, constant, predictable. Something that made objects fall, that kept planets in their orbits, and that seemed to have nothing to do with time. Space was one thing, time was another. Gravity acted on bodies, but the clock ticked on, indifferent. That picture, too, was an illusion. When Einstein extended relativity into the domain of gravity, something even more radical happened than with motion. space-time ceased to be a rigid stage. It became dynamic, flexible, capable of deformation. And when space curves, time cannot remain untouched. Gravity does not merely attract objects. Gravity modifies the rate of time. This is not a poetic metaphor or an elegant way of speaking. It is a literal statement. Time passes at different rates in regions with different gravitational strength. A clock located near a large mass ages more slowly than one located far away from it. And the most unsettling part is that you do not need extreme speeds for this to happen. It is enough to be in a different place. This is where many people feel that physics has gone too far. They accept that motion can affect time, because that seems dynamic and active. But to accept that simply standing still, supported near a mass, changes how you age, that is deeply disturbing. Yet the universe does not consult our preferences. Einstein reached this conclusion by following a surprisingly simple idea. If space and time form a single entity, and if gravity affects space, then it must also affect time. It cannot do one without the other. To separate them would be to return to the original mistake. Gravity is not a force in the classical sense. It is a curvature of space-time caused by mass and energy. Objects are not pulled in the Newtonian sense. They follow the most natural paths within a deformed geometry. And those paths include time. Imagine an elastic surface. You place a heavy ball in the center and the surface sags. Now you roll a marble nearby. It does not fall because someone pushes it, but because the terrain is deformed. This example has been used so often that it has almost become a cliché, but it contains a deep truth. Geometry dictates motion. What is usually omitted is that in space-time, this deformation does not affect only spatial directions. It also affects the temporal direction. Near a mass, the terrain of time stretches. That means that, compared with a distant clock, a clock deep in a gravitational field accumulates less proper time. It ages more slowly, not because it malfunctions, not because it mechanically lags behind, but because its temporal trajectory is different. Taylor and Wheeler express it with striking clarity. Gravity does not only curve the space through which you move, it curves the time through which you advance. Time is not immune to the weight of the universe, and I want you to feel this directly. Right now, as you read this, your clock is being affected by Earth's gravity. The time that passes for you is not the same as the time that would pass for a clock located very far away, floating in deep space. The difference is tiny, yes, imperceptible to your body, but it exists, and it has been measured. This point is crucial. We are not talking about theoretical speculation. Atomic clocks placed at different heights confirm that time passes faster the farther you are from a mass. Even a difference of a few meters is enough to detect it with modern instruments. Time at the top of a mountain passes faster than at sea level. Pause for a second with that idea. Not as a scientific curiosity, but as a physical fact. Two people, at rest with respect to each other, living ordinary experiences, can age at different rates simply by being in different places. There is no relative motion, no exotic accelerations, just gravity. Brian Greene insists that this phenomenon forces us to definitively abandon the idea of time as something uniform. Time does not depend only on how you move. It depends on where you are. Your location in space-time matters. This adds a completely new layer to our understanding of duration. It is no longer enough to talk about trajectories. We have to talk about temporal landscapes. regions where time runs faster and regions where it runs slower. Although even saying that it runs is no longer entirely correct. Time does not flow, it curves. Hawking explains that in the presence of intense gravitational fields, this curvature becomes extreme. Near very massive objects, such as dense stars or black holes, the rate of time slows dramatically. From far away, it appears as though time almost stops. From within, everything continues as normal. That contrast is essential. The clock near the mass never feels that its time is slow. It ticks normally. Its physical processes occur with the same subjective regularity. The difference appears only when it is compared with another clock located in a different gravitational region. Once again, the clock you carry with you is always right. This may seem like a repetition of time dilation due to motion, but it is not. Here, there are no relative velocities to explain the effect. Two clocks can be at rest relative to each other and still age differently. The cause is not motion, it is the geometry of space-time. Gravity introduces a profound asymmetry into time. And here an important conceptual consequence emerges. If time depends on the gravitational field, then there is no global time even for observers who are not moving relative to one another. The universe offers no common clock, not even at rest. The notion of a time of the universe becomes definitively untenable. This forces us to reconsider even ideas as basic as the age of the universe or the time elapsed since the origin. Such statements always imply a choice of reference, a specific kind of observer, a specific kind of clock. The universe keeps no single set of accounts. Now I want to take you a bit further, without losing contact with you. Think of your body as a gravitational clock. Every cell, every chemical reaction, every heartbeat occurs within a specific gravitational field. Your aging is not just a function of abstract time, but of your physical relationship to Earth's mass. It is not something you can notice. It is not something you can control, but it is real. This introduces an almost poetic idea, even though physics has no intention of being poetic. Living higher is living, literally, a little faster. Living closer to large masses is living, literally, a little more slowly. The difference does not change human destiny, but it changes our understanding of time. Taylor and Wheeler point out that this phenomenon resolves an old conceptual problem. If gravity affects all physical processes, why wouldn't it affect clocks? A clock is nothing special. It is matter. It is energy. It is subject to the same laws as everything else. The surprise is not that time is affected by gravity. The surprise is that we ever thought it wouldn't be. General relativity forces us to accept a profoundly different picture of the universe. Space-time is not a passive backdrop. It is a dynamic actor. It responds to the presence of mass and energy. It curves, deforms, stretches. And that deformation decides how you age. This has unavoidable practical implications. Satellite navigation systems, for example, must correct for both velocity-based time dilation and gravitational time dilation. The clocks on satellites, being farther from Earth, run faster than clocks on the surface. If this effect were not corrected, errors would accumulate rapidly. Relativity is not an exotic theory. It is an everyday tool disguised as abstraction. But beyond applications, there is a conceptual consequence I want you to keep with you. Time is not a uniform resource consumed equally everywhere. It is a dimension sensitive to its environment. Your duration depends not only on how you move, but on where you are. The universe does not promise temporal equality. And yet, there is no injustice in this, because there is no external standard against which to compare yourself. There is no correct time that you are losing or gaining. There are different trajectories in curved space-time. The clock you carry with you does not need to justify itself. It measures exactly what it should measure, your proper duration in the place where you exist. When you accept this, gravity ceases to be merely a force that keeps you on the ground. It becomes something far more intimate. It becomes a silent influence on your aging, on your rhythm, on your relationship with time. And here, almost without noticing it, time has ceased to be a mathematical abstraction and has become something deeply physical, something that responds to the weight of the universe. In the next section, we are going to push this idea to its limit. Because when gravity becomes extreme, when space-time curves radically, time begins to behave in ways that border on the inconceivable. Near black holes, time stretches until it nearly stops. And there, our intuitions do not just fail, they collapse completely. But even then, even in the most extreme places in the cosmos, the principle remains firm. The clock you carry with you always tells the truth, not about a universal time that does not exist, but about your exact place within a universe where time, far from being absolute, is profoundly sensitive to everything that exists. I want you to come with me to the place where all the intuitions we still hold about time truly begin to break. Not slowly, not gradually. Here they shatter. Here they fail completely. Because if up to now time had proven to be flexible, relative, and sensitive to motion and gravity, in black holes it reaches its absolute limit. This is the point where time stops seeming strange and starts seeming almost impossible. For a long time, black holes were considered theoretical monsters, awkward mathematical solutions that emerge from the equations of general relativity, but which many preferred not to take too seriously. They were so extreme that they seemed unreal. Today we know they exist, that they are not rare, that there are millions of them scattered throughout the universe, and that, far from being mere cosmic curiosities, they are natural laboratories where space and time reveal their deepest behavior. A black hole is not just a very massive object. It is not simply a collapsed star. It is a region of space-time where curvature reaches such an extreme level that intuitive rules stop working. Not because the laws break, but because they are expressed without compromise. To understand what happens to time near a black hole, we have to start with a key idea: the horizon. The event horizon is not a physical surface. It is not a wall. It is not a solid boundary. It is a causal boundary, an invisible line in space-time that separates two regions with radically different properties. Beyond that line, nothing can ever influence the outside again. Not matter, not light, not information. And here comes the first blow to common sense. The horizon is not special from a local point of view. If you were falling toward a sufficiently large black hole, you would notice nothing special as you crossed it. There are no jolts, no cosmic alarms, no dramatic moment marked on your clock. The time you carry with you continues to advance normally. But from the outside, the story is completely different. Imagine that you observe from afar someone falling toward a black hole. You never see them cross the horizon. Never. As they approach, their motions appear to slow down more and more. Their signals arrive increasingly weakened, more redshifted, more stretched in time. From your point of view, the traveler's clock slows down extremely. Each of their seconds seems to last longer and longer. Time for them appears to freeze right at the edge of the horizon. Here, a phrase often repeated in popular science appears: time stops at the horizon of a black hole. But that phrase is dangerous if it is not properly understood, because time does not stop for the one who falls. It stops only from the point of view of the distant observer. And this distinction changes everything. What you are seeing here is not a failure of the theory, but a brutal demonstration of something we have already learned. There is no universal time. There is no single rhythm shared by everyone. Each observer has their own time, and in the presence of extreme gravity, those differences become infinite, literally infinite. Time dilation near a black hole does not grow without limit because something special happens at the horizon. It grows because space-time curvature becomes so intense that the temporal trajectories of different observers separate radically. For someone very far away, the clock near the horizon never quite finishes ticking its last second. It always seems to be about to, but never does. The time of the falling object stretches endlessly. From the outside, the black hole seems to freeze time. From the inside, nothing extraordinary happens. Hawking emphasizes this point with particular care. There is no contradiction because there is no privileged point of view. The distant observer and the falling observer describe different realities, but both are valid in their context. The mistake would be to try to impose a single temporal narrative. Time does not collapse, it fragments. This is where the notion of the horizon becomes truly profound. It is not just a spatial boundary, it is a temporal boundary. It marks the point beyond which the futures of different observers can no longer be reconciled. The horizon is not where time stops. It is where futures stop being shared. This has unsettling consequences. From the outside, the falling object seems to remain suspended forever, approaching the horizon ever more slowly. From the inside, it crosses without difficulty and continues its trajectory toward even more extreme regions. Both accounts are correct, and they cannot be combined into a single one. Brian Greene explains that this situation is not a visual trick or an optical illusion caused by signal delays. It is a real difference in the structure of space-time. The clock near the horizon accumulates proper time in a perfectly normal way, but its relationship to distant time becomes increasingly distorted. Time dilation becomes infinite because space-time allows it. I want you to pause here for a moment, because this idea carries enormous conceptual weight. We have gone from relative time to time dependent on motion, then to time affected by gravity, and now to a time that can separate without limit between observers. There is no solid ground to return to. The black hole is not an isolated anomaly. It is an inevitable consequence of allowing gravity to act without restrictions. It is what happens when space-time curves to the extreme. And here arises a question many avoid asking. What does now mean near a black hole? The honest answer is that the question loses its meaning. There is no coherent way to define a common present between a distant observer and someone near the horizon. Their slices of space-time do not overlap. Their notions of simultaneity cannot be reconciled. Time ceases to be something we can synchronize even in principle. This leads to a deeply unsettling idea. From the point of view of the external universe, everything that falls toward a black hole seems to remain frozen in a kind of eternal present, piling up near the horizon. From the point of view of the falling object, that eternal present does not exist. The journey continues. The universe tolerates both realities without conflict. Taylor and Wheeler emphasize that this behavior is not exclusive to black holes. but an extreme amplification of something already present in general relativity. Time has always been sensitive to geometry. The black hole merely pushes that sensitivity to the limit. There is no magic here. There is coherence taken to its ultimate consequences. And yet, emotionally, it is impossible not to feel vertigo, because black holes force us to accept that time can stretch to infinity, that it can separate without limit between observers, that it can almost stop without violating any fundamental law. Time is not fragile. It is flexible to extremes our minds were never prepared to imagine. At this point, the clock you carry with you remains faithful. For the one who falls, it ticks normal seconds. It does not freeze. It does not break. It does not subjectively slow down. But that clock can no longer be compared to the clock of the external universe in any simple way. The agreement breaks definitively. In the second part of this section, we will venture even deeper into this territory. We will talk about what happens beyond the horizon, about the singularity, about the limits of time as we understand it, and about why, at these extremes, physics itself begins to run out of clear words. Because black holes do not only push time to its limit, they also show us where our theories themselves begin to fall short. And there, time ceases to be merely strange and begins to become truly mysterious. Now we move forward, right to the edge of what seems like the end of time itself, the singularity of a black hole. That point where the laws of physics, as we know them, do not merely stop being useful, but break completely. To get there, we need one more small image. Imagine a clock sitting right at the edge of a black hole, where gravity is so intense that the curvature of space-time becomes infinite. Everything you can observe from the outside appears to slow down until finally it stops. But here's the trick. From inside the black hole, the clock continues to function normally. For the one who falls in, nothing seems to change. Time keeps passing as it always has, even though the observation from the outside is completely different. This point where time seems to come to a complete halt is not just a mathematical curiosity. It is the place where our equations, which explain space-time so well under more gentle conditions, collapse. Inside a black hole, time and space merge into a state in which it no longer makes sense to speak of them separately. The singularity is not simply a region of high gravity. It is a place where space-time becomes completely incomprehensible. Upon reaching the center of a black hole, we encounter what Taylor and Wheeler call a gravitational singularity. This is a point where the curvature of space-time becomes infinite, a place where distortions of space and time are so extreme that the laws of general relativity cease to be valid. In other words, the physics we understand up to that point can no longer explain what happens there. What is most unsettling is that, at the singularity, not only are space and time distorted, they dissolve. Instead of a clear distinction between past, present, and future, everything seems to collapse into a single point. And most disturbing of all is that this point, from our perspective, is a place where time and space are lost in a kind of infinitely compressed state. But not everything is chaos inside a black hole. If you follow the world line that falls toward the singularity, you realize that for the observer inside, everything unfolds as usual. Along that path toward the center, the traveler encounters the paradox that, although they are crossing an absolute limit, their proper time continues to flow normally for them. Nothing feels strange. It does not feel as though time is stopping. In fact, there is nothing inside the black hole that could indicate that time has stopped. Everything proceeds according to the traveler's clock. From the outside, on the other hand, everything appears to slow down more and more. The traveler seems to freeze at the event horizon, as if the universe were observing this final moment of their life in an eternally frozen state. This happens because, in relativistic terms, the time seen by the external observer is nothing more than a projection of their own time, distorted by the enormous curvature of space-time created by the black hole. In reality, from inside the black hole, time continues to exist, but in a form so altered and so disconnected from the rest of the universe that we cannot compare an now inside with the one outside. This is one of the most terrifying features of black holes. They are not only points of no return, but points where the rules of time and space cease to be comparable to those we experience in everyday life. And here, the true paradox emerges. Somewhere inside the event horizon, distortions of space-time become so intense that what was once present can no longer be separated from what was once future. Particles fall toward the singularity at a rate we cannot even perceive. But for them, there is no almost eternal present like the one the external observer sees. What is happening inside the black hole, in some sense, continues along its normal course. The problem is that when we try to see what is happening from the outside, our physical tools and our intuitions are completely blocked. This makes the singularity even more fascinating. It is not just a point of infinite gravity, but a place where time curves to such an extent that the very sequence of events no longer makes any sense. No matter how many calculations we perform, or how many theories physics attempts to use to explain what happens inside the singularity, at that point, the physical laws as we understand them collapse. To confront this singularity, today's physicists have had to turn to an entirely new field, quantum gravity. This is an area of research that seeks to merge Einstein's general relativity with the quantum theory of subatomic particles, in an effort to understand what happens at the extremes of space-time where both theories meet. Quantum gravity is still in its infancy, but it is one of the keys to unraveling what happens inside black holes. Physicists dream of a theory that can unite the two great forces of nature, gravity and subatomic interactions. At the singularity, these two forces must combine in a way we have never been able to observe directly. It is at this point that modern physics must take a great leap, because the laws we know, so perfectly valid at human and cosmic scales, break down completely inside black holes. It is fascinating to imagine that everything we know about the universe might be insufficient at the singularity. There is so much we do not know, so much we do not understand, yet so much that is essential if we are to truly grasp how time and space actually work. The singularity, with its infinite density, is also an open door to the unknown, a place where the laws of the universe become unrecognizable and where our concepts of time and causality simply no longer apply. In this sense, a black hole is not merely a cosmic curiosity. It represents the very edge of our limitations as human beings, trying to understand the ungraspable. It is the place where the limits of time as we know it break down, where distortions become infinite, and where what can be observed from the outside has nothing to do with what happens inside. Thus, when we look at a black hole, we are not only observing an extremely dense concentration of matter, but a place where the rules of physics and time, as we understand them, cease to exist in any comprehensible way. Black holes teach us that, in the deepest extremes of space-time, time loses its ordinary meaning, and everything we thought we knew about how existence unfolds collapses in the face of the singularity. And yet, this is only the beginning of the story. Because if a black hole shows us how time bends, twists, and almost stops, it also reminds us that, ultimately, the universe is far more mysterious than our everyday understanding can encompass. I want you to think about a simple cup of coffee. You placed it carefully on the table while thinking about something important. Maybe you are about to drink it, or maybe you already have. In any case, at some moment, the cup falls and breaks. And although the scene happens in the present, there is something in your mind that has already anticipated what is about to come. The sound of porcelain shattering, the coffee spilling, the chaos that follows. That is something we take for granted. We live it every day. Coffee spills, things break, disorder appears. But why do we remember what has happened and not what is yet to come? Why does the arrow of time always point in one direction, from back to front? Why do we not remember the future, even though, scientifically speaking, it is allowed by the laws of physics? This is one of the deepest and most puzzling mysteries of time, and one of the most human aspects of our experience of reality. The arrow of time is not just a way of measuring the duration of events. It is a question of how we perceive the order of things. And that arrow, which always points toward the future, is tied to a fundamental concept in physics: entropy. Entropy, in simple terms, is a measure of disorder in a system. The greater the entropy, the greater the chaos. And in a deep sense, it is what drives the arrow of time. The second law of thermodynamics states that in any physical process, the entropy of an isolated system tends to increase over time. Things become disordered. Coffee spills. Chaos grows. Particles spread out in more disordered ways. If you throw a die, the chances that all its faces will land in a perfectly ordered and organized way are minimal. Chaos, by contrast, is far more probable. Now, before you think physics is becoming too philosophical, I want you to know that this has very real physical implications. It is one of the reasons why the past and the future feel so different to us. The arrow of time, the one that forces us to move forward, is a direct effect of entropy. The way things evolve over time depends on how particles and systems tend toward disorder. Think of a tidy room. If you leave it alone for a while, it is unlikely to remain orderly on its own. Instead of following a specific pattern, the particles that make up the objects in the room, the air molecules, the dust, spread randomly through space. This is a manifestation of entropy. Things tend toward disorder, and this seemingly simple but profoundly important process becomes the reason why we remember the past but not the future. The reason lies in the temporal asymmetry we observe in the universe. The universe is full of processes in which entropy increases. In most natural processes, the future is more disordered than the past. In other words, the past has more structure, while the future is destined to be more chaotic. And therefore, we remember the past clearly because it is full of patterns and structures that allow us to access it. The future, however, is uncertain and chaotic, and that is why we cannot remember it as something already lived. Einstein, in his famous equation, showed us that time is not a universal constant, but something that depends on the observer and on each trajectory. But the arrow of time, the fact that we can remember only the past and not the future, is not due solely to the curvature of space-time. It has to do with how entropy governs the evolution of the universe. This growing disorder of the universe is not just a matter of objects around us, like the broken cup mentioned earlier. It is a fundamental property of reality itself. When the universe was born, about 13.8 billion years ago, it was in a state of extremely high order. Particles were concentrated in a very small, very dense region. Over time, particles moved apart, stars were born and died, galaxies formed and expanded. And as they did, the entropy of the universe increased. Each of those processes, each stellar explosion, each galactic expansion, moved toward a more disordered future, a future in which the possibilities for order became increasingly small. And of course, if we go backward in time, the universe appears to be in a much more ordered state. Particles were far more concentrated. Entropy was much lower. And this difference between a low entropy state at the beginning of the universe and a high entropy state at the end is what gives rise to the arrow of time. This concept is not only philosophical, it also has very real consequences in our everyday lives. Why can't we rewind time and correct our mistakes? The answer is that every time a system changes, entropy increases. When we try to reverse a change, we are essentially trying to reduce a system's entropy, which is extremely unlikely to occur without an external input of energy. Take the simple act of breaking a cup. When it falls to the floor, it shatters into pieces. In terms of entropy, we have gone from a low entropy state, an intact cup, to a high entropy one, pieces scattered across the floor. The reason we cannot make the cup return to its previous state is that restoring that low entropy would require an external intervention, an energetic process to gather all the pieces together, something highly improbable in a closed system. It is far more likely that the pieces will continue to spread into disorder. The arrow of time is not just an abstract concept of theoretical physics. It is present in every one of our everyday experiences. What we perceive as the arrow of time is a direct manifestation of the increase of entropy in all systems in the universe. This is the process that makes memory possible, because the past is full of low entropy structures we can recognize. The future, however, is far more uncertain, far more chaotic, and that is why we cannot remember it. To make this clearer, imagine two events in the universe. The first is an explosion at the center of a galaxy, a supernova. At the moment it occurs, that explosion is an event of extremely high energy, an enormous release of entropy. But what matters to us now is not the explosion itself, but the fact that the future of the universe is shaped by the expansion and dispersion of the matter and energy released in that explosion. The second event is a process that occurs inside your brain when you remember the past. Memory, neuronal activity, recollection, is the result of an increase in entropy within your biological system. Your neurons reorganize themselves to record the past and allow you to reconstruct it. Without increasing entropy, there would be no memory, no history. And most importantly, the future is filled with uncertainty because entropy has already reached levels so high that we cannot predict details with precision. Entropy is the reason the future cannot be remembered. It is the reason the arrow of time always moves forward and never backward. The increase of entropy generates the direction in which time moves, from organization toward chaos. And this arrow cannot be reversed without external intervention, without an expenditure of energy that reorganizes things, something that is nearly impossible in the natural universe. This is why the universe always tends toward chaos, not because chaos is the final destiny, but because entropy continues to increase, making the future more uncertain and less ordered than the past. Events in the future become more probabilistic, more disordered, and that is what gives rise to our experience of the passage of time, an irreversible flow toward disorder. This takes us to a deep place. If the past is full of order and the future is full of disorder, why don't we see a total collapse into entropy at the universal level? The answer is that the universe began in a low entropy state and is destined to move toward disorder, but not in a way that robs time of meaning. On the contrary, the increase of entropy is what gives coherence to the passage of time and to our experience of the present. In the next part, we will see how this arrow of time connects to what happens at the quantum level, how particles and the smallest systems follow this universal rule, and why, even in the subatomic world, entropy remains the force that drives time. Because ultimately, the passage of time and entropy are two sides of the same coin, and what we understand as past and future is only a reflection of that deeper reality. Now, I want you to take one more step, not toward the large, but toward the small, toward something so tiny that it no longer resembles anything you have ever experienced. Until now, we have spoken about time in terms of trajectories, gravity, clocks, and the cosmos. All of that was already strange, but it still retained something familiar. There was still continuity. There were still stories that could be told from beginning to end. In the quantum world, even that begins to fracture. Here, time not only ceases to be absolute, it stops behaving like a clear line. Before and after, categories we use without thinking become fragile, blurred, sometimes impossible to define with precision. Not because physics is incomplete, but because reality, at its deepest level, does not seem to be organized according to our narrative intuitions. Stephen Hawking points out something essential from the outset. The fundamental equations that describe the quantum world do not clearly distinguish between past and future. They work the same way if you reverse the direction of time. In their basic form, they contain no built-in arrow. The arrow of time we experience is not born there. It emerges elsewhere. This should already make you slightly uncomfortable, because it means that, at the deepest level we know, the universe does not know what the past is and what the future is. That distinction appears later as an emergent phenomenon, not as a fundamental law. In quantum mechanics, what exists are not well-defined trajectories, like classical world lines, but probability amplitudes, possibilities, superpositions. A system is not in a definite state until something happens that forces it to be defined. And here a dangerous word appears: measurement. Measurement is not a passive act. It is not simply looking at what was already there. In the quantum world, measuring is intervening. It is forcing a choice. It is breaking a superposition of possibilities and producing a concrete outcome. Before measurement, the system does not have a definite value for many of its properties. It is not in a clear state in the classical sense. After measurement, it is. Something has changed irreversibly, and that irreversibility is key to understanding time. Brian Greene insists that the fragility of before and after in the quantum world does not mean that time disappears, but that it ceases to be a rigid sequence of well-defined facts. Before measurement, it makes no sense to ask with certainty what exactly happened. Afterward, it does. The before is not a blurred version of the after. It is a different reality, governed by probabilities, not by facts. This collides head-on with our everyday way of thinking. We are used to believing that things always had a definite state, even if we did not know it. Quantum mechanics says something far more radical. In many cases, that definite state did not exist. It was not hidden. It was not waiting to be discovered. It simply did not exist as such. Here, time begins to behave in a profoundly strange way. Because if there is no definite state before measurement, what exactly does before mean? Before what? Before the system has a concrete reality? Taylor and Wheeler approach this carefully, avoiding simplifications. At the quantum level, time is still a parameter in the equations, but its physical interpretation changes. Time no longer orders a sequence of well-defined events. It orders the evolution of probabilities. What evolves are not facts, but possibilities. This means that the quantum past is not a fixed list of things that happened, but a set of potentialities that only became concrete when they interacted with something larger, something classical, something irreversible. The macroscopic world, the one you inhabit, acts as a brutal amplifier. When a quantum possibility comes into contact with a large environment full of degrees of freedom, the superposition breaks. The system becomes locked into a result. Time at that moment acquires direction. The arrow of time emerges when indeterminacy turns into fact. Hawking points out that this transition is not fully understood, but its connection to entropy is clear. Measurement, decoherence, the effective collapse of possibilities always involve an increase in entropy. Information disperses, correlations are lost, order degrades. Quantum time has no arrow of its own. The arrow appears when the quantum world connects with the thermodynamic world. And here, I want you to pause for a moment, because this is profound. The time you experience is not born in the most fundamental equations. It is born when the universe can no longer go back, because information has dispersed too much. Before and after are not primary categories. They are consequences. This explains why, in the quantum world, you can find processes that seem to violate our temporal intuition, particles that appear to influence each other without a clear temporal order, correlations that do not fit into a classical narrative of local cause and effect. Not because time is broken, but because we are trying to impose a structure on it that it does not have at that level. Brian Greene explains that in certain quantum experiments, trying to assign a clear temporal order to events is not only difficult, but incorrect. The system does not decide what happened first until the entire experimental setup is defined. Time stops being a line and starts to resemble a network of relationships. This does not mean that everything is arbitrary. Causality does not disappear. You cannot send signals into the past or violate cause and effect relations in the macroscopic world. But at the quantum level, causality is expressed in a subtler, less narrative, less human way. Here, another quiet intuition breaks. The idea that the universe always has a perfectly defined history, even if we do not know it. At the deepest level, that history is constructed as it happens. The past was not always there waiting to be remembered. In many cases, the past becomes fixed when the present interacts with it. This is almost unbearable for the classical mind. We like to think of the past as solid, immutable, completely defined. Quantum mechanics suggests that, in certain contexts, the past is more fragile than we believe. Not in the sense that it can be arbitrarily changed, but in the sense that it was not always defined with infinite precision. Taylor and Wheeler express this provocatively. The act of measurement not only creates a defined present, but selects a past consistent with that present. Not because the past is rewritten, but because only certain possible histories survive contact with macroscopic reality. Time stops being a recorded tape and becomes a construction. This does not invalidate your everyday experience. Your past is real. Your memories are fixed. Human history is not a cloud of probabilities. But at the deepest level, the solidity of the past is the result of a physical process, not a fundamental property, guaranteed from the start. Hawking even goes so far as to suggest that near the origin of the universe, the distinction between time and space may have been even more diffuse. In his quantum cosmological models, time emerges gradually as an effective dimension, not as a clearly defined initial coordinate. Time may not have existed forever. And this connects with something we have already seen. The arrow of time is not in the fundamental laws. It is in the initial conditions, in the fact that the universe began in a state of low entropy, in the fact that quantum probabilities crystallize into irreversible facts when they interact with a vast environment. Quantum time does not push, it does not drag, it does not flow. Quantum time waits for something to happen. And that something is the loss of information, dispersion, the increase of disorder. Only then does a clear before become separated from an after. This is where many people feel time slipping through their conceptual fingers. Because it is no longer a clear entity, even in principle. It is an emergent property of complex physical processes. There is no universal quantum clock setting the rhythm of the cosmos. There are transitions. There are interactions. There are moments when possibilities stop coexisting and one becomes real. And I want you to think about this from your own experience. Your consciousness works in a similar way. You do not perceive a superposition of possible futures. You perceive a defined present, built from irreversible physical interactions in your brain. Memory fixes the past. Entropy protects it. The time you feel is the result of physical processes that turn the possible into the actual. This does not reduce time to an illusion. It makes it even deeper. Time is not a trivial dimension. It is a delicate consequence of how the universe moves from possibility to reality. Brian Greene emphasizes that this view does not eliminate objective reality. The world does not depend on you observing it, but it does depend on real physical interactions that destroy superpositions and create facts. Time emerges where ambiguity disappears, and this leaves us in a fascinating and slightly unsettling place. The time you experience, the one that organizes your life, your memories, your decisions, is not a fundamental piece of the universe. It is a robust, stable, inevitable construction at large scales, but not primordial. Beneath it lies a more diffuse, more probabilistic reality, where before and after do not always make sense. Time does not govern the deepest level of reality. It is the result of that level when it becomes organized. And in the next block, we will close the circle. Because if time emerges, if the arrow appears, if the past and the future are not absolute, then the final great question is inevitable. What does all this mean for the universe as a whole? Does time have a beginning? Does it have an end? Or is it simply a transient property of a particular phase of the cosmos? There, time ceases to be only a physical problem and becomes an existential question about the very nature of reality. I want us now to widen our view until there are no individual objects, no specific clocks, no local observers. I want us to look at time from the largest possible scale, the time of the entire universe. Not your time, not mine, not that of a spaceship or an atom. The time of everything. Here, the question changes its nature. It is no longer how does time pass, but what it means for time to exist at all. For most of human history, the universe was thought to be eternal. with no clear beginning, no defined origin. Time was simply there, flowing from forever to forever. That idea was comfortable. It removed the most uncomfortable question of all. What came before? But modern physics did not allow us to keep that comfort. When we observe the universe on large scales, when we see galaxies moving away from one another, when we measure the stretching of space itself, a clear and disturbing picture emerges. The universe is expanding. And not only that, if you run that expansion backward in time, it inevitably leads to a state that is denser, hotter, more compact. Up to a limit. That limit is what we call the Big Bang. But I want you to forget for a moment the popular image of an explosion at a point in space. That image is misleading. The Big Bang was not an explosion in space. It was an expansion of space. Everything was closer to everything else. There was no center. There was no outside. And crucially, there was no before in the classical sense. Here is where time begins to behave in a radically different way from anything you have imagined. The Big Bang is not only the origin of the material universe, it is, according to our best current theories, the origin of time itself, not time measured by clocks, time as a dimension. Hawking emphasizes this point strongly because it is often misunderstood. Asking what was before the Big Bang is, in this view, like asking what is north of the North Pole. The question assumes a direction that ceases to exist at the limit. Time does not begin within the universe. Time begins with the universe. This is not a gratuitous philosophical claim. It follows directly from the equations of general relativity applied to the universe as a whole. When you extrapolate the expansion of the universe backward, space contracts, density increases, and the proper time of any observer converges toward a common origin. Not because all clocks synchronize, but because the very concept of duration stops making sense beyond that point. The Big Bang is not an event in time. It is the boundary of time. This is hard to accept because our minds are trained to think in sequences. Something happens, then something else. But here there is no then. The Big Bang does not happen after anything. It is the point from which after begins to have meaning. Brian Greene explains this carefully. Time is not a container in which the universe appears. Time is a property that emerges along with space and matter. Before the Big Bang, there is no before waiting to be filled. This does not mean we cannot talk about the origin of the universe. It means we must do so using a language different from everyday intuition. The time of the universe is not an infinite line stretching into the past and the future. It is a dimension that can have a beginning, a structure, and perhaps an end. Here, another deeply unsettling idea appears. If time had a beginning, could it have an end? The expansion of the universe gives us clues. We know that space is stretching. Galaxies are moving apart. Energy is thinning out. Entropy is increasing. Everything points toward a future in which the universe will be colder, emptier, more uniform. A universe in which interesting things no longer happen. This is sometimes called the heat death of the universe. Not a final explosion, not a violent collapse, but a gradual exhaustion. A state in which differences disappear, where there are no energy gradients to drive complex processes. And here, time once again plays a strange role, because time, as we experience it, needs change. It needs processes. It needs contrasts. In a completely uniform universe, time loses content, not because it ceases to exist mathematically, but because it no longer has events to mark it. The time of the universe may not end with a dramatic final moment. It may fade into irrelevance. Taylor and Wheeler emphasize that the proper time of observers is tied to their trajectories, but cosmological time is something else. It is a way of organizing the global history of the universe, a useful coordinate for describing its evolution from early states to late states. That cosmological time begins at the Big Bang, and its arrow is defined by expansion and by the increase of entropy. The young universe was hot, dense, full of contrasts. The old universe is cold, diluted, close to equilibrium. That transition gives direction to cosmic time. But here, an even deeper question arises. If time begins at the Big Bang, what exactly does beginning mean? It does not mean that something appears out of a prior void. It does not mean that the universe is created within a pre-existing temporal stage. It means that the very structure that allows us to speak of before and after emerges at that boundary. Hawking even proposed models in which time, near the Big Bang, behaves more like a spatial dimension. There is no clear temporal direction, no defined arrow. Only when the universe expands sufficiently does time acquire its familiar character. In that sense, the beginning of time is not a single instant, but a region where our usual categories stop working. This has an enormous conceptual consequence. Time is not the backdrop of the universe. It is part of the script. The universe does not happen in time. Time happens with the universe, and this forces us to rethink even the idea of causality. If there is no time before the Big Bang, there can be no earlier temporal cause. Causes, as we understand them, require time. They require a before and an after. The origin of the universe cannot be explained as an effect caused by something earlier in time, because time itself is involved in what begins. This does not eliminate deep questions. It transforms them. We no longer ask what caused the Big Bang before, but rather, why does this space-time structure exist instead of another? A question that points more toward fundamental laws than toward a temporal sequence. Brian Greene emphasizes that this does not mean the universe is inexplicable, but that our explanations must abandon classical temporal narratives when approaching the limits. Time has a domain of validity. Within the expanded universe, time organizes history. At the initial boundary, time ceases to be a useful tool. And here I want you to connect this to yourself. Your life unfolds within a tiny slice of cosmic time, an almost negligible instant compared to the age of the universe. And yet, your experience of time is so intense, so real, so full of meaning, that it is hard to accept that time itself is not fundamental. But the universe is not obligated to conform to our psychology. The time you live is real, but not absolute. It is a local manifestation of a much larger structure. When we speak of the beginning of time, we are not talking about a first second marked on a universal clock. We are talking about the boundary beyond which the notion of duration begins to make sense. Before that boundary, the question itself ceases to be well posed. This is not a defeat of thought. It is a lesson in humility. Time is not infinite into the past. It is not eternal by necessity. It is an emergent property of a particular phase of the universe. And that makes it even more extraordinary, because it means that time, far from being a passive stage, is a delicate consequence of how the universe exists. And here, almost without noticing, we have closed a complete arc. We began believing that time was obvious, uniform, universal. We discovered that it depends on motion, on gravity, on trajectory, on measurement, on entropy. And now we see that, on the cosmic scale, time itself has a history. It was born, and it could, in some way, cease to be relevant. In the final block, we are going to do something different. We will not add more physics. We will look at everything we have traversed and ask the inevitable question: what does it mean to live in a universe where time is not what we thought it was? How does it change our position, our humility, our way of understanding existence? Because in the end, understanding time is not only an intellectual achievement, it is a way of better understanding who we are within a cosmos that does not revolve around our intuitions, but around laws far deeper and more surprising. Now I want you to return to yourself, not to the laboratory, not to the distant cosmos, not to atomic clocks or black holes, to you here, reading this. Because after everything we have traveled through, after dismantling one by one our most intuitive ideas about time, the inevitable question is not physical, it is human. What does all this change in the way we live? For almost your entire life, you have treated time as an adversary, something that slips away, that is lacking, that presses, that runs out. We say that time runs, that time catches up with us, that time comes crashing down on us. We live as if time were an external force chasing us or a resource that drains without permission. But none of that is true. Time is not an enemy. It is not even a river flowing against you. Time is the dimension in which you exist. You are not inside time the way you are inside a room. You are a trajectory in space-time. Your life does not happen a long time. Your life is time. This changes something deep. If time is not absolute, if it is not universal, if it is not the same for everyone, then it no longer makes sense to compare yourself to an ideal clock, to an external rhythm, to a measure you are supposedly failing to meet. There is no correct time that you are wasting. There is your proper duration, the one you traverse with your body, your history, your decisions. The clock you carry with you is always right. Throughout this journey, we have seen that time depends on motion, gravity, trajectory, environment, interaction, even on the state of the entire universe. Nothing about time is rigid. Nothing is simple. Nothing is guaranteed except one thing: your local experience is valid. That should bring relief, because it means you are not failing. When time feels fast or slow, you are not wrong when a year seems to evaporate and a minute feels eternal. That elasticity is not merely psychological. It is a real property of time itself. Time does not betray you. It behaves exactly as the universe allows it to behave. We have also seen something even more unsettling. Time is not fundamental. It is not at the deepest foundation of reality. It emerges. It appears when the universe organizes itself in a certain way. It is born with expansion, with entropy, with the loss of information, with irreversibility. That means time is not a cruel entity stealing things from you. It is a consequence of things happening. Without change, there would be no time. Without processes, there would be no duration. Without history, there would be no past. Time exists because the universe allows something to happen, and that gives each moment a different value. Not because it is scarce, but because it is real only while it occurs. The present is not an infinitely thin line between past and future. It is a living region, continuously built by irreversible physical interactions. To be alive is to participate in that construction. When we understand that there is no universal now, that there is no present shared by the entire cosmos, something shifts inside us. Our present stops being small. It stops being insignificant. It is the only one that exists for our world line. You are not arriving late to the universe. You are exactly where your world line has taken you. It also changes how we think about the past. We have learned that the past is not simply a fixed archive that exists independently of everything. At the deepest level, the past becomes fixed when the present interacts with it. Memory, history, identity are physical processes that require irreversibility. To remember is not to travel backward. It is to reconstruct, in the present, a structure established by entropic processes. This does not make the past false. It makes it precious, because it means the past exists insofar as it has left real traces in the world. Physical traces, traces in matter, traces in you, and those traces are not trivial. They are the result of a deep direction in the universe. The future, by contrast, is not written because it cannot be, not because it is magical, but because the physical process that fixes it has not yet occurred. The future is not a closed book waiting to be read. It is a cloud of possibilities waiting for interaction. That should also change your relationship with it. The future does not threaten you. It owes you nothing. It is not watching you from ahead. The future does not yet exist as concrete reality. It exists only as potential, and you participate in its construction. When we stop seeing time as a rigid line and start seeing it as a dimension through which we move, something softens. Artificial urgency loses its grip. The anxiety about making the most of time transforms. It is no longer about squeezing it, but about traversing it. You do not run against time, you move with it. We have seen that even the universe as a whole has its own time, that it was born in a state of low entropy, that it expands, that it moves toward an increasingly uniform future. Cosmic time is neither eternal backward nor necessarily dramatic forward. It is a phase, a story. And within that immense story, your life is not an anomaly. It is a natural consequence. Your consciousness, your memory, your perception of flow exist because the universe allows local arrows of time. It allows systems far from equilibrium. It allows something to be ordered for a while. That is what you are, a temporal island of order in an ocean that tends toward equilibrium. It is not tragic. It is extraordinary. When you accept that time is not an external enemy, but the very form of your existence, you begin to live differently, not faster, not slower, more present. The present is not an instant slipping away. It is the only place where your world line can feel something. The past cannot be changed, not as punishment, but because it has already been fixed by real physical processes. The future cannot be fully controlled, not out of impotence, but because it does not yet exist as fact. That leaves a clear space, now, not as a slogan, as physical reality. Here is where your duration is built. Here is where your time is real. Here is where the universe, for a moment, happens as you. In the end, understanding time does not give you more hours. It does not lengthen your life. It does not freeze aging. But it does something deeper. It frees you from a mistaken relationship with it. Time does not chase you. It does not judge you. It owes you nothing. Time is the dimension that makes it possible for something to matter. And as long as your clock keeps ticking, as long as your trajectory continues, as long as the universe allows this small region of order that is you to exist, time is not a limit. It is the space in which your existence takes place. And that may be the most human and most honest way to bring this entire journey to a close.